Good morning, students. So, last class we have seen about synchronous motor basic principle, the constructions of synchronous motor. Already we have seen synchronous motor under no load conditions, how armature current changes with DC excitation to rotor. Based on this one, we have studied how the back EMF plays a vital role to produce prime mover power. And at the same time, we also seen the power flow diagram in synchronous motor, how electrical energy AC supply given to the stator. This electrical energy, how it is converted into mechanical energy as an output. During this process, what are the losses takes place inside of the motor, we have seen. Finally, the mechanical power developed for phase also we have seen and calculated few problems. Then first case, the prime mover power developed in the motor is equal to EB into V by ZA cos theta minus alpha minus EB square by ZA cos theta, where alpha is the load angle and theta is an internal angle, phi is a power factor. At the same time, the internal, that is the load angle, the maximum is 90 degrees. If alpha exceeds 90 degrees, pull out torque develops and synchronism breaks, rotor comes to standstill condition. At the same time, the impedance angle also calculated theta, that is constant, tan inverse of XA by RA. We can say that is also internal machine angle, and when theta is equal to alpha, that is the condition for maximum power developed in synchronous motor. At the same time, we are also assumed that if resistance of the armature is very low as compared to the armature reactance, then we simplified this power developed, mechanical power developed in the motor is equal to PM is equal to simple back EMF voltage divided by XA into sin alpha. Based on these simple applications, we have calculated few problems. Now, let us do the another performance calculations with vector diagrams, how the induction motor draws when load is applied on this one, only lagging power factor from the supply. But whereas in our synchronous motor, for the same load, for the constant load, whether full load, off load and no load condition, how this armature current changes from lagging power factor to unity power factor, from unity power factor to leading power factor, draws from the supply. That means how this synchronous motor works as a synchronous condenser under no load condition, under minimum load condition with over excitations. Now, how this armature current changes during this period, how the power factor also changes if excitation changes. This performances is done with the help of one experiment in our laboratory. I think you have to do this V and inverted V curves of a synchronous motor. This experiment is very simple, easy, simple by changing DC excitation to the rotor at constant supply voltage, at constant speed. Anyway, the synchronous motor runs at at constant speed only. During this period, by changing field excitation, you are going to observe the armature current value also changes, as well as its power factor also changes. This can be tabulated and draw a graph. This shows similar to the English alphabets V curve. If excitation versus armature current. If same excitation current changes with corresponding to input power factor of current taken, then we are going to get inverted V curve. It shows that how the armature current as well as the power factor behaves in lagging power factor and leading power factor under normal excitation condition. That means under excitation condition, over excitation condition, normal excitation condition, how these values, two values, armature current and its power factor changes with field current. Let us see one by one in detail. Now, V and inverted V curves of synchronous motor. Let us introduce myself. Myself, Dr. C.H. Yadaya, Senior Lecturer in Electrical and Electronics Engineering at Government Polytechnic, Husnabad. Today topic regarding to the 5th semester diploma students, C18 EE 503 curriculum. Main subject is synchronous motors. In that subtopic is V and inverted V curves. Let us recall what we have seen previous classes. In previous periods, we have discussed the effect of excitation on armature current and power factor theoretically. This motor, this armature current and power factor changes by excitation of rotor DC supply under normal excitation, under excitation, over excitation we have seen. From that we have studied some salient points. What are those salient points? Some important points stand out clearly from the above discussion, previous discussions. That is very essential and easy. Once again recall it. The magnitude of armature current varies with excitation. The current has a large value both for low and high values of excitation. That means under excitation, over excitation condition, armature current value takes from the supply is large quantity. In between, it has a minimum value corresponding to a certain excitation. That means you are going to required excitation as to give the induction synchronous motor as per your convenience. For the same input supply, armature current varies over a wide range and causes the power factor also to vary accordingly. As we know that power input is equal to root 3 VL IL cos phi. Motor is the same and root 3 is the constant and voltage where applied is a constant. A changing factor is the IL cos phi. The load current and power factors is inversely proportional to each other. For the same supply voltage, for the same load on the motor, by changing excitation, the current value changes by keeping power factor as a constant value. One case, if current constant, flux changes. So both cases we are taking in two cases. We are concentrating in first case by changing field excitation, input DC supply, how the armature current changes from large value to minimum value and minimum value to large value, how it changes by changing the field current to the rotor from initial to some final value. Similarly, we are going to observe same thing concentrating on power factor, how the power factor changes from starting to initial field current to final field current. This is a very familiar, this is a vector diagram. So V is the applied voltage, EB is the back EMF induced in the stator conductors due to the field of rotor. The field of stator rotating magnetic field axis, the field of rotor magnetic axis, theoretically both are coincides at the condition of synchronization condition. Stator and rotor poles are coupled, interlocked each other, magnetic locking takes place in ideal condition under no load condition. But practically there is a inherent losses, iron losses, friction and windage losses, some amount of the copper losses to meet from supply. So that purpose we require some torque is required. The torque may not be produced if these two axes are coincide each other, that alpha is equal to 0, because the magnitude of supply voltage and induced back EMF is equal but 180 degrees apart. There is no resultant voltage, ER is equal to 0. Hence, we are assuming that small amount of the gap between difference between stator axis and rotor axis, that we say load angle, coupling angle alpha. Due to this one, we are going to get a resultant ER. Correspondingly, the current IA at angle of theta. Theta is almost internal angle, almost constant, that is equal to tan inverse of XL by RA. And also we have seen whenever excited motor runs with leading power factor, that means over excited condition, motor runs on leading power factor which is connected in parallel with the other motors in industries to improve the power factor, and with lagging power factor when under excited condition. If induction motors are less, then we are going to use, this is a simple synchronous motor under excited condition. The power factor is unity for approximately at normal excitation to the rotor. Power factor is changing, either increasing or decreasing in the excitation condition. Armature current is increased with respect to decrease in power factor. These all points we have covered in previous classes. Now, today objectives: upon the completion of this period, you would be able to know the plotting of V curves and inverted V curves with experimental procedure. How we are going to draw these curves in laboratory, let us discuss in this class. And after getting V curves and inverted V curves, let us analyze what is happening in synchronous motors, that is importance of V curves and inverted V curves. What do you mean the V curves? Now, if the armature current IA is plotted against excitation or field current IF for various load conditions, we obtain a set of curves known as V curves. Due to their shape similar to English alphabet letter V, we can say these are V curves. That means here you can see here, normally it will takes current from supply, input supply. We are going to 3-phase, here 3-phase supply, 440 volts, 50 Hz AC supply is given to our synchronous motor. It will draw a current of IA at power factor of cos phi. And we loaded motor some constant load. For example, this is a loaded 10 kilowatts motor. We loaded a 50 kilowatts, for example. So, 5 kilowatts off load we added on the motor. The motor is running. That means once again, let us assume the motor having a capacity of 10 kilowatts motor. Now, motor is started with some excitation. The load on the motor is 5 kilowatts. At that condition, if you are observed, what is the input current, armature current? With the help of the ammeter connected in series in any one phase. Then at the same time find the what is the power factor of motor with help of the PF meter. At the same time observe what is the value of excitation current IF from rotor side. Okay. Now if that's the first reading. Now here the excitation current IF goes on increases, then observe what is the armature current, what is the PF power factor changes with corresponding to changing field current from minimum value to maximum value of the field current flows in rotor coils. The flux also changes. This influence on stator and it induces back EMF. This back EMF always opposes the applied voltage correspondingly. So it changes its armature current as well as its power factor. This is a theoretical one. Now same thing we are going to observe here. Okay. So simply assume that here the armature current and PF changes corresponding to IF. If IF versus armature current, we know that V curves. If field current versus power factor, we are going to inverted V curves. Simple. Once again, if field current corresponding to armature current, we are going to V curves. Field current versus power factor, we are going to inverted V curves. Simple. So let us see. Now here you can observe V curves. If the field current is taken is the x axis and correspondingly armature current is the y axis. Then how the curve is taking place by changing the field current from small value to higher value. For this, in experiment level, in laboratory we have to do. So we require the synchronous motor and we require the some pony motor, that is an induction motor, to start the synchronous motor initially. After starting, then we are going to excite it and stator and rotor interlock each other. Motor runs at a synchronous speed, then decouple the input prime mover, that a pony motor. Then our motor is running as a synchronous motor. At that condition, you have observed what is the input current from the stator side by using one ammeter connected in any one phase. At the same time, you connect one power factor meter in stator side and you connect one ammeter in rotor DC supply side. Now load on motor is continuously running, applied some load and don't change this load, and at the same time maintain the input supply constant by using variac. Then the speed automatically maintained constant. For example, 1500 RPM for 4-pole machine. The motor is running 1500 RPM. The voltage is taking 400 volts AC supply. Now field current is given initially, so 0.0 2 amperes, for example. Now at this condition, take down the readings on ammeter, armature current and power factor meter reading. Then second case, vary the variac of DC supply rheostat, increase the field current from 0.2 amperes to 0.3 amperes. Then wait for 10 seconds. Then note down the armature current as well as its power factor from power factor meter. You should remember whether it's a power factor is changing from lagging to leading, whether it's taking lagging side, leading side on power factor meter. Note down that thing. Now third reading, further increase field current of rotor side by changing the rheostat. Then what is the reading? Now in this case 0.4 amperes IF. Now correspondingly stator side, note down the ammeter reading and power factor meter reading. Further change rheostat 0.5 amperes, then take down the ammeter reading and power factor meter. Now go on changing in field current. So 1 ampere, 2 ampere, 3 amperes up to what is the rated field current of rotor side. Then you take the nearly 10 to 12 readings continuously. You can observe the armature current initially high value, that is goes on decreasing one stage. At the same time, power factor also it can go on increasing, you can observe it. At one stage, the needle of the power factor meter also comes to the from lagging power factor to unity power factor, then goes on increasing further. The power factor as well as the armature current changes. Now the current starts increasing. At the same time, power factor moving on leading scale, then goes on increasing up to rated field current of rotor circuit. Note down all readings. Then comes to normal position, switch off the main supply. Now based on taken readings, we are going to draw the curves. Now what we have observed, the V curves of synchronous motor shows how the armature current IA varies with excitation for the same input supply. The synchronous motor V curves for no load condition and off full load condition. Full load are drawn. Here you can observe, for example, this synchronous motor, what we have discussed in just now. So same thing in with help of the figures. Now this is a synchronous motor rated 10 kilowatts. Now first case, there is no load on the motor. Motor is running normally. We connected stator side, one ammeter, one PF meter, power factor meter, and here rotor side we are connected one rheostat and one ammeter. By changing rheostat, the field current changes. Note down the ammeter reading and power factor reading. up to 10 readings. Goes on changing rheostat. The current changes from 0 to its, for example, 5 amperes field current. Then correspondingly note down the what is the armature current and power factor in each step of changing the rheostat. 3 readings. That is the one set of the readings. Now after taking this reading, comes to now add the load. That means instead of 10 kilowatts capacity of the motor, we add 5 kilowatts load on motor. Then repeat the experiment from 0 amperes to rated amperes with steps. Each step take the once again armature current and power factor by varying variac. Note down the readings on a tabular form. After getting rated field current, now add the full load, nearly 10 kilowatts load on motor. Now once again start the changing rheostat from initial position to rated field current and note down the armature reading and power factor in steps. So now from 1 to 10 readings, by changing the field current, correspondingly each step we have taken armature current and power factor. First case, no load condition. After taking 10 readings, we added 50% of the load on the motor. Once again we started from initial field current to maximum field current and taken 10 readings. Similarly, if full loaded on the motor and started from 0 amperes to full field current, we taken the further 10 readings. So based on this tabular forms, under no load condition, under off load condition, under full load condition, the armature current and power factor, how it varies with corresponding to changes in field current of rotor circuit. Then analyze it. I think you have some idea. Now based on this tabular serial number, the field current and armature current for the V cause. Serial number 1, field current may be 0.5 amperes. At that condition, what is the armature current? Whether it is a 2 amperes, 3 amperes or 5 amperes based on 10 kilowatts. P is equal to root 3 VLL by cos phi. So we are going to get the rated current. That may be nearly what is the current, you can take it. Then under no load condition, what is the armature current? That is current under no load, even it draws the current from the supply to meet the inherent losses, iron losses, some part of the copper losses and friction and windage losses purpose. And you take the power factor also, the other table, same table, serial number, field current and PF. Another column is going to PF. Correspondingly, you take the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 readings for the, because number of readings is required for the smooth curve. After taking this tabular forms, and we are going to draw, here is x axis take as a field current and y axis take as a armature current for V cause, first case under no load condition. Now take the first point, go on, place on the points how the armature current initially is the maximum. If the current increases, this value also changes. Simple, you note down the point out the points on a graph sheet. Then you can observe how the field current changes, the armature current also decreasing. Now further increase the field current, then what will happen? So here it is a current increasing. Now further increase the field current, then what will happen? The armature current goes on raising. At one stage field current, suppose for example just you take it one rubber band. If rubber band is stretched to a limit value, it stretches perfectly. If applied further force, automatically it will break it. Similarly here also you are going to apply the required field current, then it works. Armature current draws is a minimum value. If further increases field current, then automatically due to the magnetic field it saturates. Even if you are increasing, then automatically it is going to saturate the coils, as well as the armature current also increases. But one thing changes in this machine, that is the power factor goes from lagging to leading power factor. Now first case we are going to draw the V cos. Now you can observe the points on a graph. It shows similar to the V letter of English letter. Connect this all lines, then we are going to V. So this is simple. Okay, so simple, you take the readings and plot on a graph by taking x axis as a field current, y axis as a armature current with a confined scale, and point the points on a graph sheet and join the line. You are going to get one curve. That curve seems like a English alphabet V letters. So it shows a V cos. Okay. Now at center you can see the field current, which is in the middle here. At that condition here you can observe. So this is the minimum current at this condition, armature current, and this is the field current at this. That means we have to operate field current at this condition, and at this condition the minimum armature current. Ideally that is a UPF condition, unity power factor condition. Now here what is happening? This area is a lagging power factor, under excitation, low field current. Here is a required excitation. If further increased, then goes on increasing, the armature current also increasing, and in this case power factor is the leading power factor, leading. That means this area is a leading range, this area is a lagging range, this area is a UPF range. So we can say this is a under excitation, this is a over excitation, and this is a normal excitation condition. For here another one load condition. This is a no load condition. If 50% added the load on the motor, then with the same tabular we are going to get another curve. So we are going to get the another curve and apply the 3/4 75% on this one, 75% of the load. Then we are going to get another curve. 100% we are going to add the load, then we are going to get the curve. So these are the calls based on the load of a synchronous motor. Let us discuss this one clearly. Now you can see here what you are discussed in previous. So here this is a unity power factor curve, and this is a lagging power factor area, this area, and this area is a leading power factor area. This is the unity power factor area. Now you can see this violet color is a low load condition. We are going to get V cos. In this case, the current is drastically in a straight line, but here in this is the curve due to the curvature due to magnetic saturation. If I go on increasing, automatically core will saturate because it's a ferromagnetic materials. Now, if load is increasing, some off load, we are going to green color. If full load, if we are going to get the blue color. That means here the armature current under no load condition is a very low value, and here is a off load, here is a full load condition. You can see that this is the armature current, this is the IF. Okay, this is simple one. Now same we are elaborated here. Okay, so this is V cos. So normal excitation condition and no load condition, off load condition, full load condition. How these curves are changes. Okay, so this area is a lagging power factor, this area is a leading power factor. Now let us draw another tabular, that is called field current versus power factor. If the power factor is plotted against excitation for various load conditions, that may be no load, off load, full load conditions, we obtain a set of curves known as inverted V cos. Similarly, same experiment already we have taken, same by changing this field current IF, then here we are taking power factor meter, PF meter reading, PF reading, change it, take it, change it, take it, change it, take it. Correspondingly, what is the field current, what is the power factor? We take the 10 readings in the tabular form. Okay, then draw the curve. Here same field current, here y axis now taken as a power factor PF, y axis. Take the corresponding reading and substitute indicate the values based on the tabular form. Now what will happen? The lines are, if field current increases, it is going on increasing. Now further increases field current, then it comes to the minimum value. So now join the lines. So we are going to get one curve. It shows a inverted V in a alphabets. So it is known as a inverted V curve of a synchronous motor. What it predicts, what it showing, that means the field current initially, you can see here, initially this is a value at the IF, the field current at this condition, the power factor is minimum. If field current increases, then power factor also raising, then we are going to UPF power factor, unity power factor at this condition. Now if further increases, then automatically the power factor reducing. Okay, so here you have to observe this thing. Then this is the minimum field current is required motor which is runs on UPF, unity power factor, and similar to the, from this line, left side is the lagging power factor and right side is the leading power factor. So this is a one curve drawn based on our readings under no load condition. How this changes, you can see it. Initially here, initially what is the power factor and initially what is the field current. If field current increases, the curve is go on increasing up this condition. Here is the IF, required IF, and here is the UPF under no load condition. If further increases, then power factor goes on decreasing. But field current increased under no load condition. If 50% of the load, the curve changes. Now you can see the here you can observe one thing. This is a field current at no load. Now this is a field current changes from this place to this place. Some more field current is required more to maintain to get the UPF. Here is a UPF, unity power factor, and this is a lagging, this is a leading area of this curve. Now off load. Now if under full load condition, you can see it's changed from left to right to get the unity power factor. Now 1, 2, 3, this are the field currents going to get UPF with changes the no load to full load. But 3 curves are showing as a inverted V shape. Now you can see this the second unity power factor, and this area is a lagging power factor, this area is a leading power factor. Okay, this is a normal excitation conditions. So salient points of inverted V cause. From inverted V cause, it is observed that the power factor is lagging when the motor is under excited condition and leading when it is over excited. In between, the power factor is unity. So these are the things we have discussed. Now what we have seen in this class? So we have seen in this class, we have discussed about importance of V cause and inverted V cause. That means how the power factor as well as the armature current we are going to maintain optimum by keeping our DC supply, DC current to the rotor, and by changing armature current and power factor, we are going to change the consumption of the motor also. The V cause of synchronous motor shows how the armature current varies with excitation for the same input values. Inverted V cause of the synchronous motor shows how the power factor varies with the excitation with the same supply. Based on this performance, we are going to maintain our synchronous motor in our industries to improve the power factor of our industries, where nearly 70% of the induction motors available for different applications, which always draws lagging power factor. So with the help of our synchronous motor and induction motors are connected in the same line in parallel, but our induction motor is operated based on required power factor. So overall, our all induction motors and transformers are given same line which are drawing lagging power factor, and that means which consumes the reactive power, whereas our synchronous motor generates a reactive power, that is called kVA or generating. Reactive power generated by our synchronous motor, reactive power consumed by induction motors and transformers. So this reactive power consumption and generation effect on power factor of the factory. So we are going to imposed to maintain the power factor 0.85 lag, or sometimes we require to maintain the unity power factor to avoid the excess current from supply, as well as the to perform our motors up to full extent rated values. Now time comes, we will close it here. We will see next topic in the next class. Thank you.